Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Hello and welcome back. We are so thrilled to have you with us for this because today we're embarking on a journey that is going to fundamentally change how you picture, everything.
That's a big claim to start with.
It is, I know. And I don't mean everything like, your job or your relationships. Though honestly, this might make you feel so small, it changes that too.
Yeah.
I mean, the actual physical architecture of the reality we all live in.
It's true. We're talking about our home today. And not just Earth, not just our solar system, but our entire galactic home, the Milky Way.
And more than that, the neighborhood it's in. Because we all have this mental image of the Milky Way, don't we? It's this beautiful glowing spiral just floating.
A lonely island in a sea is nothing.
Exactly. Like a frisbee thrown into a pitch black room. It's just sort of there.
Yeah.
Drifting in the void, we think of space as this big empty bucket that we're just rattling around inside.
And that's the picture you see in textbooks and planetariums. It's this romantic idea of solitary galaxy. But the research we're exploring today, which was just published yesterday, January 27th, 2026, it completely shatters that image.
It turns out we're not just floating in some random void. We have an address. A very, very specific, massive, and almost completely invisible address. We're not just in space. We are inside something.
We are. And finding that address, understanding that specific location, actually solves a mystery that's been keeping astronomers up at night for about 50 years.
50 years. That's a long time to be confused about your own backyard. That's generations of scientists staring at the same data and just going, wait, this doesn't add up.
In cosmology, 50 years is practically a cold case. And this particular cold case, among astronomers, it's known as the mystery of the two quiet neighbors.
I love that name.
Yeah.
Sounds like a suburban crime novel. The neighbors were quiet? Too quiet.
In a cosmological sense, that's exactly what it is. It's a puzzle about motion, and it's a puzzle about gravity. The central question is, why does everything around our galaxy move so perfectly, so exactly the way the Big Bang predicts it should, when, by all rights, the laws of gravity say it should be a complete mess?
And the answer, which we are going to unpack today, involves building a virtual twin of our universe.
Yep.
It involves a massive invisible sheet of matter that we are apparently surfing on, and these vast, almost terrifyingly empty spaces called cosmic voids.
It sounds like science fiction, but this is hard data coming from the University of Groningen, published in Nature Astronomy, which is one of the most prestigious journals out there.
This is the real deal.
It is, and it's one of those discoveries that feels so satisfying. It doesn't just give us a new piece of trivia, it makes the entire picture finally click into place.
It really does. So for today's exploration, and we are calling this an exploration, I want everyone listening to just strap in. We're not just looking at data points today. We're going to try to visualize the invisible architecture of our little corner of the cosmos. We're going to map out our cosmic geography.
I like that, cosmic geography. Just like you need to know about mountains and oceans to understand history on Earth, you have to understand dark matter sheets and voids to understand the history of our galaxy.
Okay, so let's set the stage. To understand why this is such a huge deal, we first need to understand the before picture. Let's talk about the local group. It sounds like a neighborhood watch committee.
It sort of is for galaxies. The local group is our immediate family in the universe. Space is vast, but galaxies, they tend to cluster together. We're not alone.
And the Milky Way? We're one of the big ones in this group.
We're one of the two titans. We have a sibling. A big sister, actually.
Andromeda.
The Andromeda galaxy. She's a bit bigger than us, maybe a little more massive, depending on how you measure it. But the two of us, we are the dominant gravitational players in this region.
But it's not just the two of us, right?
Yeah.
There are others in the house.
Oh, absolutely. Surrounding us, two giants are dozens of smaller, what we call satellite galaxies, mostly dwarf galaxies.
Nothing like the Toro moons for our galaxy.
That's a perfect way to think of it. They're caught in our combined gravitational web buzzing around us. The Large and Small Magellanic Clouds are the most famous ones you can see from the southern hemisphere. We're all bound together by gravity. We're a family unit.
Okay, so we're a gravitationally bound family. We're all holding hands. Now, let's zoom out a bit. Because to get to the mystery, we have to understand the main rule that the rest of the universe follows. If we look past our family, what are all the other families doing?
They're all moving away. That's the big rule, expansion. Almost 100 years ago, Edwin Hubble and Georges Lemaitre figured out that the universe is getting bigger.
The Hubble-Lemaitre law. We hear this all the time, but let's just really break it down for a second. What does it actually mean on a practical level?
The observation itself is actually remarkably simple. If you look at any distant galaxy and you measure the light coming from it, you'll see that the light waves are stretched out.
They're redshifted.
They're redshifted. It's the Doppler effect for light. And that stretching tells us that the galaxy is moving away from us.
Like the sound of a siren dropping in pitch as an ambulance drives past you.
Exactly like that. But here's the crucial part Hubble noticed. There's a pattern. The further away a galaxy is, the faster it's moving away from us. A galaxy that's twice as far away is receding twice as fast.
So it's not that galaxies are flying through space like bullets, it's that the space between everything is stretching.
Precisely. The classic analogy is drawing dots on a balloon and then blowing it up. From the perspective of any one dot, all the other dots appear to be moving away. This is the bedrock evidence for the Big Bang. If you run that movie in reverse, everything crunches down to a single point.
Okay, so the rule of the cosmos is expansion. If I look out my window with a telescope, I should see cosmic red taillights everywhere. Everyone is driving away. That's the standard flow.
That is the Hubble flow. That is the general rule. But there's always a but in physics, isn't there?
There usually is.
And there is a very, very famous exception to this rule sitting right on our doorstep.
Andromeda again.
Andromeda again. If you measure the light from Andromeda, it is not red-shifted. It's blue-shifted.
Which means it's coming toward us. It's not driving away. It's flooring it in our direction.
It is barreling toward the Milky Way at a speed of about 100 kilometers per second.
Okay, 100 kilometers. Little second. Can you put that in perspective for me? That number is just, it's too big.
Okay, imagine traveling from New York City to Philadelphia. That's about 150 kilometers. So Andromeda covers that distance in 1.5 seconds.
It's unthinkable. A rifle bullet travels at, what, maybe 1 kilometer per second?
If that. So this is an entire galaxy with hundreds of billions of stars moving 100 times faster than a speeding bullet. And it's aimed right at us.
So we're due for a collision.
We are. In about 4.5 billion years, our two galaxies will merge. It'll be a spectacular cosmic event. The night sky will be completely transformed as these two spirals tear each other apart and reform into one giant elliptical galaxy.
But why? Why is this happening? If the whole universe, if the fabric of space-time is stretching, why are we getting closer to Andromeda?
Because on a local scale, gravity is stronger than the expansion. The Milky Way and Andromeda are just so massive and we're relatively close to each other, only about 2.5 million light years apart.
Only 2.5 million light years.
In cosmic terms, that's next door. Our mutual gravitational pull is so strong that it completely overpowers the gentle stretching of the universe between us.
Okay, I get that. So locally, we're a bound system. Our little family unit is holding hands so tightly that the expanding current of the universe can't pull us apart.
Exactly. We are gravitationally detached from the Hubble flow. We're our own little island of gravitational stability.
Okay, so gravity pulls things together, expansion pushes them apart, a cosmic tug of war. I'm with you.
Now, here is the mystery. Here is the puzzle that has bothered astronomers for 5 decades. To see it, we need to look just outside the local group.
The neighbors just over the fence.
Right. Not our little satellite galaxies, not Andromeda. We're talking about the next set of galaxies out. They're close enough that they should still feel the immense gravity of our local group.
Because we're a giant gravitational sinkhole, right?
Yeah.
The combined mass of the Milky Way and Andromeda is huge. If I'm a galaxy just drifting past, I should feel that pull.
You absolutely should. Newton's laws of gravity don't just stop at some arbitrary boundary. So we would expect our gravity to be tugging on these nearby galaxies. It should be slowing down their retreat. Or it should be pulling them off course, making their movements messy, chaotic.
It's like if you're trying to run away from someone and they manage to grab the back of your shirt. You might still get away, but you're going to stumble. Your path won't be a smooth, straight line.
That is a perfect analogy. And in astronomy, we call those stumbles peculiar velocities. Peculiar just means a velocity that's particular to the local gravity, not part of the general cosmic flow. We expect the galaxies right next to us to have very high peculiar velocities. We expect to see a total mess.
But I'm guessing, based on the setup here, that we do not see a mess.
We do not. That's the whole problem. For 50 years, observations have shown that these nearby galaxies are moving away from us almost perfectly. They follow the Hubble-Lemaître law to the letter. Their motion is incredibly smooth. It's suspiciously quiet.
So they're acting as if we, this entire massive local group, aren't even here.
Precisely. It's as if our gravity just magically switches off at the property line. And physically, that makes absolutely no sense. Imagine you place a heavy bowling ball on a trampoline. The fabric of the trampoline curves down, right? It creates a deep well.
Of course. That's the classic visualization of gravity warping space-time.
Now imagine you roll some marbles past that bowling ball. What should happen?
They should curve inward. They should be deflected by the dip in the trampoline. Their paths should change.
Exactly. But what we see in the cosmos is the equivalent of those marbles rolling in a perfectly straight line, as if the bowling ball and its huge gravitational well weren't there at all. They just cruise past, completely ignoring the massive objects sitting right next to them.
That would drive me insane. It defies basic physics. Mass creates gravity. Gravity affects motion. End of story. Why aren't we affecting them?
It drove astronomers crazy. It's been called the deviation problem. Why are the motions in our local universe so cold, so quiet, so orderly, when we have this enormous concentration of mass right here that should be stirring everything up? It's a huge anomaly.
It sounds like a glitch in the matrix. Like someone forgot to turn on the physics engine for our particular sector.
It's funny you mention a simulation, because to finally solve this 50-year-old puzzle, that's exactly where these researchers had to go. They had to build a simulation.
So let's talk about the team that cracked the case.
Yeah.
We have the lead researcher, Iwud Wempe, who was a PhD student at the time, and Professor Amina Helmi, both from the Kaptein Institute in Groningen.
That's right. And they had collaborators from Germany, France, and Sweden. It was a big international effort to solve this very local problem.
And their big idea was that just looking through telescopes wasn't cutting it anymore. People had been doing that for decades. They needed a new approach. They needed to build a universe from the ground up.
They did. They set out to create what they call a virtual twin of our local universe.
A virtual twin. I love that term. It sounds like something from engineering, where they build a digital replica of a jet engine to test it before building the real one.
And it implies a kind of precision that is. It's incredibly rare in cosmology. Usually when we simulate the universe, we're dealing with big statistical averages. We create a huge generic box of the universe, we throw in the right ingredients, and we let it evolve.
And you get a universe.
Yeah.
But not our universe.
Exactly. You get something that statistically looks like ours. It has the right number of galaxies, the right kind of clustering, but it's not our specific reality. It doesn't have the Milky Way right here and Andromeda right there, moving in just the right way.
It's like having a stock photo of a family. It looks like a family, but it's not your family. The stock photo can't tell you why the floorboard in your specific living room squeaks.
That's a great way to put it. This team needed a simulation that reproduced our specific reality down to the details. They needed to recreate the cosmic crime scene exactly as it is today.
How do you even begin to do that? The universe is so complex, you can't just type "create Milky Way" into a computer and hit enter.
No, it's much more subtle than that. They used a really clever technique that works both forwards and backwards in time. They started at the very beginning. They started with the baby universe, using data from the cosmic microwave background.
The CMB, just remind us quickly what that is again.
The CMB is the afterglow of the Big Bang. It's the oldest light in the universe, from about 380,000 years after the beginning. And what it gives us is a map. It's a map of how matter was distributed when the universe was just an infant. It wasn't perfectly smooth. There were tiny, tiny variations. Some spots were a fraction of a degree warmer, meaning slightly denser, and some were cooler.
And those slightly denser spots are the seeds that eventually grow into galaxies and galaxy clusters.
They're the seeds of everything. Gravity takes over, pulling more and more matter into those denser regions, and over 13.8 billion years, they blossom into the cosmic structures we see today. So the researchers took that initial map, that primordial seed, and they plugged it into a supercomputer.
And then they just hit fast forward.
Essentially, yes. They applied all the known laws of physics, gravity, dark matter interactions, the expansion of space, and they let this baby universe grow up. But here's the thing. The universe is chaotic. A tiny, imperceptible change in those initial conditions can lead to a completely different universe 13.8 billion years later.
A butterfly effect on a cosmic scale.
Exactly.
Yeah.
So they couldn't just run the simulation once. They had to run many, many variations, tweaking the initial conditions ever so slightly. They were searching for a very specific outcome. They needed to find a simulation that ended up with a Milky Way and an Andromeda that had the correct masses, were in the correct positions, and were moving toward each other at the correct speed, that 100 kilometers per second.
Just that part alone seems impossible. It feels like trying to win the cosmic lottery.
It's incredibly difficult. But they went even further. This is the part that just blows my mind. They constrained the simulation so that it also had to match the observed positions and velocities of 31 specific galaxies just outside our local group.
31. Wow. So they weren't just trying to get the two main characters right. They had to get the entire supporting cast in the right place, doing the right thing.
It's like trying to simulate a hurricane and demanding that it not only hits the right city, but that 31 specific trees in that city bend in exactly the right way at the right time. It is an extraordinary level of constraint.
It's looking for a needle in a haystack of possible universes.
It is. They had to sift through countless virtual universes to find the one that perfectly matched our own. But they did it. They actually found it. They successfully created a virtual twin.
And once you have that twin, that's where the magic happens.
Yeah.
Because you can look under the hood, you can see all the parts that are invisible in the real world.
That's the power of it. In the real universe, we have a huge problem. Most of the matter, about 85% of it is dark matter. And it's invisible. We know it's there from its gravitational effects, but we can't see it. We can't touch it. We are essentially stumbling around in the dark trying to map a landscape we can't see.
But in the simulation,
you know where every single particle of dark matter is. You put it there. You can just flip the switch and say, okay, computer, make the dark matter visible.
And when they flipped that switch, when they finally looked at the distribution of the invisible stuff in their perfect virtual twin, they saw the answer to the 50-year-old mystery.
They did. And it was not what anyone expected.
This is the big reveal. What did they see? What does our galactic neighborhood actually look like?
They saw that we are not living in a random spherical blob of matter. We are not in a cloud. The local group, the Milky Way, Andromeda, all of us, we are embedded inside a vast, large-scale sheet of dark matter.
A sheet, like a piece of paper.
A very, very thick piece of paper. Think of it as a flattened structure, a pancake, or a wall, a flat extended plane of mass.
And how big are we talking? What's the scale of this cosmic pancake?
It extends for tens of millions of light years. It's an absolutely colossal structure.
So if you could zoom way, way out from our galaxy and put on a pair of dark matter goggles, you wouldn't see a ball. You'd see this giant flat sheet.
Yes. And we, the Milky Way and Andromeda, we're like two blueberries baked into the middle of this pancake. We are sitting right inside this enormous flat layer of invisible mass.
Okay, so we're in a pancake. But pancakes have a top and bottom. There's space above and below them. What's above and below our dark matter sheet?
Voids.
Voids. That sounds empty.
It is. The technical term is also the literal description. The simulation showed that our sheet is sandwiched between two enormous regions of emptiness. Vast expanses where there are almost no galaxies and very, very little matter at all.
So let me try to visualize this. We have this dense, flat plane of dark matter and galaxies that we live inside. And if you were to travel up or down relative to that plane, you would just hit nothing for millions of light years.
For millions and millions of light years, you'd enter what we call the local voids. It's like living on a very thin, very large island in the middle of a gigantic empty ocean that extends in both directions.
Wow, that is simultaneously claustrophobic and agoraphobic. We're sort of trapped in this thin wall of stuff between two endless empty rooms.
It's a very striking image, and it fits into our broader understanding of the cosmic web. We know the universe's large-scale structure is made of filaments, walls, and voids. This research tells us our specific address. We live in a wall. We are part of the dry wall of the universe.
And this specific architecture, this sheet and these voids, this is the key to solving that gravity paradox we talked about.
It is the absolute key. The simulation showed that this is the only geometry that works. If you have a random blob of dark matter, you get the messy motions everyone expected. But if you have this specific flattened sheet structure, you get the unnervingly quiet motions that we actually observe.
Okay, let's connect the dots. We have the sheet, we have the mystery of the quiet neighbors, and the bowling ball that doesn't seem to affect the marbles. How does the sheet explain why those nearby galaxies are ignoring our gravity?
It all comes down to a gravitational tug-of-war that basically ends in a perfect stalemate.
Okay, walk me through the physics of that.
Right. So take one of those nearby galaxies. It's sitting just outside our local group. The local group itself is incredibly massive, so we are pulling on that galaxy. We're pulling it in toward us.
Okay, that's the grab the back of the shirt part of the analogy. We're slowing it down.
Exactly. But now we know we're not just an isolated clump. We are part of this huge sheet that extends far beyond that galaxy. There is a massive amount of dark matter further out in the sheet on the other side of that galaxy.
Okay, so there's mass behind it too.
A huge amount of mass. So that galaxy is essentially sandwiched. We, the local group, are pulling it in one direction, and the rest of the massive sheet is pulling it in the other direction. It's being pulled out.
So we pull it toward us, and the rest of the sheet pulls it away from us.
Precisely. And the simulation showed that those two opposing forces almost perfectly cancel each other out.
They balance.
They mask each other's effects. The net gravitational force on that galaxy from within the plane of the sheet is close to zero. So the galaxy is free to just coast.
So it just follows the general expansion of the universe as if there were no major gravitational forces acting on it at all.
Because the forces are there, but they're pulling equally from both sides. It's not that there's no gravity, it's that there's balanced gravity.
That is so elegant. It's brilliant. It's not a violation of physics. It's a consequence of a very specific geometric arrangement of mass.
It's a dynamic equilibrium. Imagine standing exactly in the middle of a narrow hallway with two giant fans at either end, both blowing at you with the exact same force. You might not move at all, but that doesn't mean there are no forces acting on you. The forces are huge, but they sum to zero.
Okay, that makes perfect sense. But you mentioned the voids were also part of the solution, the empty spaces above and below the sheet. How do they fit into this illusion of calmness?
They are just as important. This is the second piece of the puzzle. Think about where those messy, chaotic, peculiar velocities usually come from in a galaxy cluster.
They come from things falling into the cluster from all directions, right?
Exactly. If you have a big spherical cloud of matter, you expect other things to be falling toward it from the sides, from the top, from the bottom, from every possible angle. It should be raining matter.
You'd have galaxies coming in from all over the place.
And that infall would look very messy in our data. We'd see galaxies with peculiar velocities coming from every direction. It would be a very hot or dynamic system.
But we don't have matter above and below us. We have voids.
And you can't have rain if there are no clouds.
There's nothing to fall.
Precisely. The directions from which you would expect to see messy infall from above and below the plane of our sheet are empty. There are no galaxies there to be seen falling in.
So the data looks clean because the parts that would make it messy are just empty. There's no data there to begin with.
Exactly. The observations we make are naturally biased toward the galaxies that lie within the sheet. And those are the very galaxies that are caught in that perfect gravitational tug-of-war. The whole system is constructed in a way that hides its own gravitational influence.
That is an incredibly clever solution to a 50-year-old problem. It's not that the physics is wrong, it's that our local geography is filtering what we're able to see.
Yes. The researchers concluded that this flat mass distribution is the only shape that simultaneously explains the massive local group, the collision course of Andromeda, and the quiet, orderly flow of the neighboring galaxies. It all clicks into place if and only if we live in a sheet.
This has to feel like a huge validation for a lot of people. I was reading some of the quotes from the paper, and Professor Amina Helmi, one of the leads, seemed really excited by this.
She was. She said something along the lines of how exciting it was that they could solve a decades-old problem purely based on the motions of galaxies. It's a real triumph for the standard model of cosmology.
It feels like it dodged a bullet, in a way.
It absolutely did. You know, in science, whenever your observations don't match your theory, you face a choice. Either your theory is wrong or your understanding of the specific situation is incomplete.
And it's always more dramatic to say the theory is wrong.
Mm-hmm.
You see those headlines all the time. Einstein was wrong, or dark matter is a hoax.
It makes for great clickbait. And to be fair, there are some real tensions in cosmology right now. We have the Hubble tension, where different methods of measuring the universe's expansion rate give different answers. So people are actively looking for cracks in the standard model.
So when this quiet neighbors problem persisted, some people must have started to wonder, well, maybe gravity works differently on these scales. Or maybe dark matter isn't real.
Exactly. People were proposing alternative theories, like modified Newtonian dynamics, or MOND. But this research pulls us back from that ledge. It shows that the standard theory, cold dark matter, the Big Bang, general relativity, it all works perfectly. We just didn't understand our local context. We didn't know we were living in a sheet.
We were trying to solve the puzzle without ever looking at the map of the crime scene.
Right. We were treating the local group as an isolated island, when in reality it's part of a huge continent. Once you factor in the geography of the continent, the mystery vanishes. The math works.
It brings observation and theory back into perfect harmony. We don't need new physics. We just needed a better map.
And speaking of maps, the lead author, Ewood Wempe, called this the first assessment of the distribution and velocity of dark matter in the regions surrounding the Milky Way and Andromeda.
That's a huge milestone. Think about the early explorers in the 15th and 16th centuries painstakingly mapping the coastlines of new continents for the first time. That's what this is, but for the invisible landscape we inhabit.
It's a fundamental shift. We are finally moving from just cataloging points of light in the sky to understanding the underlying terrain that those lights are sitting on.
And it really contextualizes our place in the cosmic web. We've always heard that the universe, on the largest scales, looks like a web or a sponge.
Yes, a vast network of filaments, sheets, and voids.
But that was always an abstract statistical idea. Now we know, specifically, which part of the web we're in.
We do. Our address just got a lot more specific. We're in the local group, which is located inside the local sheet of dark matter, which is bounded by the local voids.
It gives you a real sense of place, doesn't it? It grounds you. Instead of just being in space, we're in the sheet. It sounds like a faction from a sci-fi novel.
It does, but it has really profound implications for how we interpret everything else we see in the universe.
Right, the so what question. Beyond being incredibly cool, why does knowing we live in a sheet matter to you, the person listening right now?
Well, it matters because our location fundamentally biases our view of everything else.
How so?
Think about it. We've just established we live in a flat pancake and there's empty space above and below us. We can't step outside of the structure to get a clear view. All of our observations of the entire universe are made from within this sheet.
I see where you're going with this. It's like living in a deep valley versus living on a high mountain peak. Your view of the surrounding landscape is completely different depending on your location.
Exactly. Or imagine trying to survey a forest. Your view is very different if you look along a dense row of trees versus looking through a clearing. Our sheet is the dense row of trees, and the voids are the clearings.
So when we look out at the most distant galaxies, billions of light years away, the light from those galaxies has to travel through our local environment to get to us.
Yes, and that environment is not uniform. If we look out along the plane of the sheet, we're looking through a huge amount of matter. We're looking through the pancake, there's more dust, more gas, more galaxies, more gravitational lensing from all that dark matter.
But if we look up or down out of the sheet,
we're looking through the voids, we're looking through the clean part of the window.
And that could affect our measurements. If we don't account for the fact that we're looking through a dirty part of the window in one direction and a clean part in another, we could misinterpret what we're seeing.
It could affect everything. It could affect our measurements of the cosmic expansion rate. It could affect our counts of distant galaxies. It might even help explain some of those other tensions in cosmology. This research is so critical because it helps us calibrate our own point of view.
We have to subtract the local effects to see the global picture clearly.
We have to understand the quirks of our own front porch before we can make grand statements about the whole neighborhood. If we assume we live in a perfectly average, random spot, our calculations will be slightly off. Now that we know we live in a sheet, we can correct for that bias.
It's a real lesson in cosmic humility, isn't it?
Right.
We thought the Earth was the center, then the Sun, then the Milky Way. Now we're realizing that even our local bit of cosmic web has a specific non-average structure that shapes our view.
The Copernican principle tells us we're not in a special place. And that's true in a grand sense. But this shows our location isn't generic either. It's specific. And that specificity matters.
Empty space isn't just empty space.
No, it has a geography. It has a landscape. Dark matter forms these sheets and filaments, and galaxies flow along them like water following the contours of a riverbed.
I really do love that idea of us living on a continent of dark matter. It makes the universe feel so much more tangible.
And it explains why our corner of it is the way it is. The quietness of our neighborhood, the orderly motions, it's all dictated by this invisible continent we're riding on.
So as we start to wrap up this incredible exploration, let's just do a quick recap of the journey we've been on.
Let's do it.
We started with a 50-year-old puzzle. Why are our galactic neighbors so quiet? Why do the galaxies just outside our local group move so smoothly, seemingly ignoring our massive gravitational pull?
We then looked at how researchers in Groningen tackled this by building a virtual twin of our universe, an incredibly precise simulation that didn't just create a universe, but recreated our specific corner of it down to the positions of 31 specific galaxies.
And when they made the invisible dark matter in that simulation visible, they discovered the secret architecture of our home. We are embedded in a massive, flat sheet of dark matter, tens of millions of light years across.
And that sheet is sandwiched between two enormous voids, two great empty spaces.
And that structure is the key that unlocks the whole mystery. The sheet creates a gravitational tug-of-war, balancing out our pull and letting nearby galaxies drift smoothly. And the voids mean there's nothing above or below us to fall in and mess up the data,
resulting in the clean, orderly, anomalously quiet flow we see today. It's not new physics, it's just cosmic geography.
a beautiful, self-consistent, and deeply satisfying solution.
It really is.
So I have one final provocative thought I want to leave everyone with. Something to chew on.
I'm ready. Lay it on me.
Okay. If we live in this quiet, stable sheet, and there are these giant empty voids on either side, it really emphasizes the difference between something and nothing. And it makes me wonder, is life itself more likely to arise in structures like these sheets? Are we here because the sheet is so quiet and stable?
That is a fascinating question. It gets right to the heart of the anthropic principle, the idea that the reason we observe the universe to have certain properties is because if it had different properties, we wouldn't be here to observe it.
Exactly.
Well, we know that the most extreme environments are probably not great for life. A giant galaxy cluster, for instance, where filaments of the cosmic web intersect, that's a really chaotic, violent place.
Right. Galaxies are constantly crashing into each other. Supermassive black holes are blazing with radiation. It seems like a tough place to build a stable solar system and have billions of years of peace and quiet.
And the voids, on the other hand, are, well, they're too empty, too lonely. It would be very difficult for enough matter to clump together to form stars and planets efficiently. You might not get enough of the heavy elements needed to build a rocky planet like Earth.
So, the sheet is the cosmic Goldilocks zone. Not too hot, not too cold, not too chaotic, not too empty.
It's entirely possible. Perhaps this quietness that puzzled astronomers for 50 years isn't just a quirk of gravity. Maybe that stability, that lack of messy infall, is a prerequisite for a galaxy like ours to gently nurture a solar system like ours over billions of years. Maybe you need a quiet street to build a home.
So the mystery of the quiet neighbors isn't just about galactic dynamics. It might actually be a clue about cosmic habitability. We are here because it's quiet here.
It might just be a quiet neighborhood is a good place to raise a civilization.
I love that. We didn't just end up here by chance. We moved to the cosmic suburbs for the good schools and the quiet streets.
And the expansive, flat, dark matter lawns.
On that note, we're going to sign off. Thank you so much for joining us on this journey through our galactic neighborhood. I hope your sense of your place in the universe feels a little bit bigger and a little more specific than it did an hour ago.
It was a true pleasure.
The next time you look up at the night sky, don't just see the stars. Imagine the invisible sheet holding it all together. Imagine the great voids above and below. And remember that the map is always, always bigger than what you can see. Keep looking up. We'll see you next time.